Next, I want to look at some applications of quadratics, and there really are a ton. So I have 3 here that I want to show you. And the first is an example of a projectile that I mentioned at the start of the videos of this section. So a projectile is an object that is thrown or kicked or even dropped that has kind of an initial speed based on maybe the kick or the throw. But then after that, there's no other energy being added to it, right? When you throw a baseball, let's say you throw that ball with that initial velocity, and then there's nothing else that's continuing to throw the ball along the way. It just kind of moves as far as it's going to go from that initial throw. So that's a projectile. So here we're going to look at a football being kicked. So when a football is kicked, the nearest defensive player is 6 feet from the point of impact with the kicker's foot. And the height of the punted football, f of x in feet, is modeled by the following quadratic. It's negative 0.01 x squared plus 1.18 x plus 2. X is the ball's horizontal distance in feet from the point of impact from the kicker's foot. Now, there is a figure on page 356. I didn't copy it into the lecture notes, but I'm just going to show it to you real quick on camera for those of you who need a little bit more background here. Okay, so here's a football player who is kicking the ball. And then here would be the first defensive player trying to block that kick, we'll say. So he's going to kick the ball up into the air. Obviously, it's not going to continue straight up forever. Eventually, it's going to go up and then start coming back down. And of course, the defensive player would love to just jump up and grab that ball and steal, right? And run the other direction. So this is what the graph is that we're looking at. So our function here gives the height of the ball. The y value is the height, how high it is in the air. And the x value represents the horizontal distance. So how far that ball is traveling horizontally instead. So that's what we're looking at here. Okay. So our first question asks, what is the maximum height of the punt and how far from the point of impact does this occur? So if you hear things like maximum or minimum, you want to really think about vertex when you're talking about quadratics. So think about this graph. Notice that in my equation, my initial value here, my a value is negative 0.01. So our a value is negative. So our graph is going to look something like this. That means that your vertex is going to occur at that maximum point. So our graph is going to be that upside down U shape, which makes sense. If you think about kicking a football or throwing an object, it's going to go up and then eventually it's going to start coming back down. So you have this upside down U shape, and your vertex is going to be the maximum height that it's going to reach. So we're going to find the vertex here. Now, this is not in vertex form, it's just in the regular form. So we need to use our equation. So we're going to use x equals negative b over 2a. Our b value here is this 1.18. So we have 1.18 negative over 2 times negative 0.01. When I go ahead and simplify all of this together, I end up with negative 59 here. So you have this negative, and then this becomes negative 59. So you end up with positive 59. And then we're going to go ahead and plug this back in. And again, we're just using our calculator here to get the value. So now I'm looking at f of 59. So I go up to my equation, negative 0.01 times 59 squared plus 1.18 times 59 plus 2. And when you multiply this all out, again, you would do your squaring first, then your multiplication. Multiplication here, what you're going to go ahead and get is 36.81. So the point that we have here is 59, 36.81. So this is my h value in my vertex, and this is my k value in my vertex. And this is a good time to maybe pause the video, try out the calculator work at home, just to make sure you know how to use your calculator and see if you're getting these same answers. So let's actually answer the question here though. It says, what is the maximum height of the punt and how far from the point of impact does it occur? So maximum height refers to maximum value here. So you want the y value for that maximum height. So our maximum height is that 36.81, and we are in feet here. The other question looks at the distance from the point of impact, so that horizontal change. So remember, the ball is traveling higher, but it's also traveling horizontally, right? So we're looking for that horizontal change as well. So how far is it from the point of impact? It is 59 feet from the point of impact. Okay. So the maximum height here, that's your Y value, and then your X value is that horizontal change. So here we're looking at the horizontal distance of how far that football travels. All right, so let's do part B now. How far must the nearest defensive player, who is 6 feet from the kicker's point of impact, reach to block the punt? So again, you kind of have to know a little bit about football here, but that person is going to kick the ball, and then you have a defensive player who's standing 6 feet away from them, from their foot, right, from that line. So they're going to kick the ball, and that player is hoping to jump up and grab that ball and intercept it, right? Or intercept it, excuse me. So what we need to figure out is, well, if that player is 6 feet away, how high would they have to jump to actually reach that ball, right? That's what really we're looking for here. So we know he's 6 feet from the player, so we're 6 feet out horizontally. That's our X value. And we're looking for our Y value, which is the height. So how high would that player have to jump in order to grab that ball? So let's go ahead and plug this in. Okay, so I'm just going to replace 6 into that formula here that I'm given, right? So we already have the model that was already created for us. And then we're going to go ahead and just simplify. So you want to do the 6 squared first, then multiply it out. And once you do all that, you're going to get, let's see, negative 0.36 plus 7.08 plus 2, and you end up with 8.72. So the player, or the defensive player, must reach 8.72 feet above the ground to block the punt. Right. So based on this kicker here, who's kicking, that's pretty high. So you'd have to be able to touch almost 9 feet in order to maybe like slap or hit or do something to block that punt or that football from going any further. So that's a pretty high jump. Or maybe not high for football players, high for me, I guess. If the ball is not blocked by the player, how far down the field will it go before hitting the ground? So let's talk about C here. What does this mean? Okay, so let's say that ball is kicked, it's going in the air, that player comes, he tries to jump up and get it, or they don't reach it, so that ball is going to continue traveling, and it's going to kind of arc, and it's eventually going to hit the ground, right? So in part C, we're assuming that the ball was kicked, the defensive player missed the kick, missed the ball, and that ball is going to continue until it hits the ground. So we're looking at the hitting the ground place here. So how far until it hits the ground? Well, when something hits the ground, typically this means that your height is equal to 0, right? Usually ground level is height 0. Again, there are a few exceptions here or there, but usually that means height of 0. So we're actually trying to find here is what's the X value when the Y value is 0. And that X value is that distance it's going to go down the field. So I'm going to take my equation, which is up here, and I'm going to go ahead and set it equal to 0. Just like that. Now I do have a quadratic to solve here. This is nothing that I'm going to even attempt to factor. If you see things like decimals or roots or fractions or anything kind of weird, you probably just want to go ahead and use the quadratic formula. So that's what I'm going to do here. I'm just going to plug everything in. So my B value is that 1.18. And that A value is that negative 0.01. And my C value is 2. All right, so we're going to keep simplifying here. Again, I just use my calculator, so I'm going to skip a couple steps, but try out the simplifying at home. So on the inside of the root, when you square this and then multiply this all out, you're going to end up canceling the negative, so you'll be adding with a positive here. You end up getting 1.4724 inside that root. And then in your denominator, you have negative 0.02. Now you end up with two answers here, right? So you have negative 1.18 plus this root. And then you also have the other version, negative 1.18 minus that root. Now, because I have so many decimals here, I'm not even going to try to simplify those roots. You just want to use your calculator here and go ahead and round. So for the first one, if you use your calculator, you get about negative 1.7. And for the second one, you get about 119.7. And remember, these are in feet. So this is one of those examples where you do have two x-intercepts, but because it's an application problem, this first one here doesn't really make much sense, right? So if you're kicking a football, you're not expecting it to go negative 1.7 feet, meaning like behind you, you're expecting it to go forward, right? And we're going to assume that that happens here, that it wasn't like a fluke or a fumble or anything like that. So the answer that they're really looking for here is not the negative value, it's going to be the positive value. So what's happening here is that football is traveling down the field, right? So here we're starting, and then it's going to end up here, and the X value here is 119.7 feet. So it's going to travel 119.7 feet down the field. So that would be our answer for C. Now, the last thing they want us to do for D is to graph this. I kind of just did a quick graph here already, so I'll do it a little bit more formally. Think about when you graph quadratics. We like to have the vertex. We like to have our intercepts. Well, I already have the x-intercept, right? I actually end up finding it here. And then I do want to have the y-intercept. So your y-intercept is when your x value is 0. So if you plug in 0 to your original equation here, you end up with negative 0.01 times 0 squared plus 1.18 times 0 plus 2. So these two parts are going to cancel out, and you end up with just 2. So that y-intercept is actually 0, 2. So what we're saying here is that ball is starting 2 feet off the ground, which sort of makes sense. If you're kicking the ball, it's not going to be directly on the ground. He's kicking it, so it's starting at 2 feet above the ground. So what's going to happen here, and I'm just going to kind of draw it real quick here, and I'll show you the picture, is you have that vertex at your maximum height here. So our vertex we saw was the point 59, 36.81. And then this value here we saw was at negative 1.7. So it's actually not really part of our example. And then here we're starting at 0, 2. So again, I'm not quite drawing this to scale, but really what's happening is that ball is going to start here and it's going to travel this way to here. Now this graph would actually keep going. So if you do the whole graph, this does continue in both directions, but it doesn't make sense after that point, right? It doesn't make sense for that ball to be underground, so to say. So you're really just looking at that part that would make sense here. And if you go into your text, I'll show you, they just have a nice picture here, much nicer, more accurate picture. So you can see here that we're just looking at the positive values. So you're starting here at 2, you're reaching that vertex, and then you're going to end here at that little over 119, right? So that's going to be that archway of that football. All right, let's do a couple more examples. That was the hardest one we're going to do, but we still have a couple other examples that are pretty nice here as well. So example 6, among all pairs of numbers, so a pair is 2, whose difference is 10. Remember, difference means subtraction. Find a pair whose product is as small as possible, right? So small, it says it right here, minimum, right? So if you hear that word minimum, and we know we're doing quadratics, you really need to figure out that quadratic so you can find your vertex. Now we're going to think of an actual equation here, but so for example, we want pairs of numbers whose difference is 10. So for example, 20 minus 10 is 10. So one pair of numbers could be 20 and 10. Or we could do 15 minus 5, which is 10. So 15 and 5 is another pair. So we want their product to be as small as possible. Well, here 20 times 10 is 200. And then we could do 15 times 5. So what's that going to be? 75. That's better, right? So we want to find the one that's the smallest combination. But we just can't guess forever. That's not going to be helpful. So we're going to set up an equation here. So let's let the first number, so let's see, first number and second number. So let's let the first number be x. Now the second number is y, but I don't want to use x and y. That doesn't help me here. So remember, I want to keep it to one variable. So what I can do here for the second number is think about the subtraction piece. And that's what I can do. So think about, well, if the first number is x, and then we're looking for the other number, we'll just call it y for a second. Well, we know that these two together are going to subtract to be 10. So we know that x minus y should be 10, right? If we subtract them here, our x and y's were 20 and 10 or 15 and 5. We want that end result to be 10. So what we're going to do is we're going to solve for the y. So I have an equation that I can use instead. So I subtract that x to both sides, divide by that -1, make sure you divide everything by -1, and we get x minus 10 as another way to express y. So instead of using y here, I'm actually going to use x minus 10 in my formula. So here's kind of a new strategy. I started with x and y, kind of find a way to relate them. I know that if I subtract them, I get the value of 10. So I'm able to use my skills of solving for a variable here to now rewrite the y in terms of x. So for my first expression, I'm using x. And then for my second expression, I'm using x minus 10. Now, the other thing I know is I want their product to be as small as possible. Well, remember, product means multiplication. So the function that I'm going to use here is going to be a product function. And I'm going to multiply my two values together, x and x minus 10. And when I do that, and I simplify, I get x squared minus 10x. So I have a quadratic here, and I know that minimum value is going to be found at the vertex. So that's maybe my next step. I'm going to find the vertex. So my a value here is going to be 1, and my b value is -10. Because my a value is 1, my graph is going to look something like this. So I know that that vertex is going to be that minimum value that I'm looking for. So I'm going to use my formula here. So I have -10 over 2 times 1. So I end up with +10 over 2, which is 5. Just cancel those negatives right away. I plug 5 back in. I get 25 minus 50, which is -25. So my point, my vertex here is 5, -25. This is my h value. This is my k value. Now we haven't actually answered the question yet, so be careful. I do have my vertex, but I do want to answer the question. So there's two parts here. The first thing I have to do is figure out the pair. Well, I know the x value, right? The x value we said was this 5 here. So if I go back to my setup, my x value is 5, and then my y value would be 5 minus 10, which is -5. So the pair is 5 and -5. Now the problem didn't say anything that they had to be positive values, just said to find a pair of numbers. So 5 and -5. And I want to know what the minimum product is. So that minimum product here is this 25, is negative 25. And you can see it here, 5 times negative 5 is negative 25. So we have our pair of values and we have our minimum product. So new technique we learned here. One was if you have two variables and you're getting stuck on how to set up the second variable, try to see if there's an equation that you can solve. We want to have our setup always be in terms of x. So you need to find a way to make everything in terms of x. So perhaps instead we do something new. Maybe we have another equation that we can use instead to solve for and rewrite that piece. All right, our last example here is going to look at area. So you have 100 yards of fencing to enclose a rectangular region. So I'm just going to start by drawing a rectangle. And I want to find the dimensions of the rectangle that maximize the area. All right. So again, I know that I'm doing quadratics here. So if I see the word maximize, I'm thinking vertex at some point, but I need to figure out my setup first. So if I have a rectangle, the area is always the length times the width. So I need a way to write the length and I need a way to write the width. So I'm gonna have to kind of figure that setup out. So if I think about my rectangle, this is a length, this is the length, this is a width, this is a width. The only thing I know is that I have 100 yards of fencing. Now, if you think about that fencing, it would have to go all the way around, right? Here, 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 and here. So actually that 100 yards is really my perimeter. So my perimeter of the rectangle is adding up all these sides. So I have 2 lengths and 2 W's, and that's going to be 100 altogether. So what I can do is I can choose one of these to be my variable. Maybe we're going to choose L to be the variable here. We'll leave it as L. And let's solve for W then. So I would subtract 2L from both sides. Divide by 2. And I get my setup is going to be 50 minus L. If you don't like using L, you can use X instead. So now I have a way that I can plug back into my formula here. And instead of using W, I'm going to use 50 minus the length. And now I can solve. So this gives me 50L minus L squared. I am going to rewrite this. So let's write it as a, we'll change it to a function of L. I do like to have my square first. So it's going to be negative L squared plus 50L. So my A here is -1 and my B here is 50. Because it's negative, I know my graph is going to look something like this. So that vertex is going to be at that maximum point here. So I'm looking for my vertex and we're not using X, we're using L here. So L would be negative B over 2A. So negative 50 over 2 times -1. That's going to give me positive 25. And then my width here then would be 50 minus 25, which is also 25. So we actually end up with a square, it looks like here instead of our two values. And we also want to find the maximum area. So if I find the maximum area, I'm going to plug my 25 back in. And let's see, I have 625. So what do we have here? The dimensions and then the maximum area. So my length is 25 yards and my width is also 25 yards. So I end up actually with a square and the maximum area is 625. And just watch your units. It's going to be square yards or yards squared here. So actually having a square ends up being the most efficient way that we can use those 100 yards of fencing, but maximize the area. So for quadratics, when you see questions with max or mins, you want to think the vertex. So you have to find some way to create a quadratic equation so that you can find the vertex. And a lot of times that's going to mean for us solving for one of the variables so that we can write everything just in terms of X or in terms of one variable. So that's going to be that starting point there. Use things that you know. So we know things like perimeter. We know things like the keywords difference and product. So think of them like puzzles. See if you can find another sort of equation that helps you out there with solving. And then once you have that equation, then you're really thinking about the vertex. And remember, the x value gives you one part of it, and then that y value of the vertex gives you that max or min value. So that's the other part here.